Let us start by looking at decision trees on tabular data. Okay, these are the basic decision trees that you're familiar with from other courses. Okay, and the idea is very simple. You have your table and you want to classify every tuple or make a prediction on every tuple. So you take the tuple and you basically apply some conditions. What is the track? Okay, if it's CS, then you go to this child. If it's CSC, you go to the other child. Otherwise, you go to the third child. And based on the answer, for example, in CS, you ask another question. Is the birth greater than 2003? And based on the answer, yes or no, you go to the next child until you reach a leaf. In the leaf, you make a decision. In our regression tree, this decision is a number. In a classification tree, this decision is a Boolean value, 0 or 1. If you have a multi-class classification, then the leaf has one of the classes in your multi-class classification. Okay, so more formally, so we have our tabular signature. Remember, it consists of a sequence of attributes and a domain or a sequence of domains, okay, DOM. And I may write DOM, or I may use this notation of DOM as meaning the product space of the domains, the one times domain, and just slight abuse of a notation. So a decision tree is basically a rooted tree where every node V having children U1 to UD is associated with a mapping. This mapping takes a tuple and maps it to one of the children, okay? So it's a function from the domain of values, of sequences of values to the children, okay? Then every leaf U is associated with a target value, our decision, okay? In a classification tree, this decision comes from a binary domain, 0, 1. Regression tree, it's the sequence of, it's a set of real numbers. Okay. The semantics of the model, as we said, is straightforward. You take a tuple, you traverse the tree, you reach a leaf, and you make a decision based on what's written on the leaf. And how you traverse the leaf, that's based on what is the child that phi v tells you to go to for every internal node v. Okay, so that's a formal definition. How do we learn a decision tree? So suppose that we have our training set T1, Y1 to Tn, Yn. So basically we do it in a greedy, iterative manner, starting with a single node. And then at each point we have a tree and we are traversing the leaves. And for every leaf, we choose whether or not to expand it, to split it. We can traverse the leaves in any uh, order. There are different approaches to how we traverse these leaves: breadth first search, depth first search, best first search, and so on. Okay, so if you reach a stopping criterion, okay, if there's some stopping criterion that applies to your node U or the leaf U, then you say, okay, I don't split it anymore. Now I need to make a decision. What is the decision? It can be the common value, average value, median of the different values, different rows, different tuples that reach this node. And that's basically the what the stopping criteria and stopping condition says. Further splitting is not worthwhile. It is worthwhile to make a decision. But if you didn't reach a stopping criterion, then you, in principle, need to consider every possible split phi u. And among these, choose the one with the maximum gain, the one where you gain the most. And we'll see later examples of gain functions. And then you split. Okay, so do we consider every condition? Well, we usually restrict to some class of conditions uh, for practical reasons, and we choose the best there from that class. Okay, ah, so this is an illustration of this process. We chose a leaf here, this one, and we choose to split it. We find a condition. Here it's birth greater than equal to 2003, and it has two answers, yes, no, and based on that we build the next tree. Okay, so this is a greedy process, at least this phase of the learning. We do not regret. When you split, we do not go back. But then we can do some post-processing. I'll discuss it later. And then we can actually regret. Okay. What are the types of conditions by which we split nodes? As I said, we usually look at simple conditions. Um, some conditions or common conditions are unary. Essentially, look at a single attribute and make some decision based on that single attribute. As opposed to, for example, looking at multiple attributes. Here, A1 greater than A3 involves two attributes. So that's more complex. Now, it doesn't mean that you cannot do that or you cannot find it in the literature. I'm just saying that the common split would look at a single attribute, would be unary. And an especially common and simple condition would be axis align, where we basically say, well, my domain is ordered by some, greater than, for example, it is in numerical. And then my condition will be AI greater or equal to C. So basically what I need to do is find which C is the best for me. I need to choose which AI to use and which C to use. And that gives me the space of split conditions to choose from. Okay, now here we're starting to see the challenges of tabular data. What if I have a categorical domain? And so we can think of various ways of dealing with the categorical domains. If you have a few values, you can split by the values themselves, like A equals CI when you have the category C1 to CD. Well, this is possible. And this is similar to saying, well, let's look at it as D different attributes using one-hot encoding, and then each attribute is binary. Okay. If your categories are naturally ordered, like low, medium, high, then you can say, well, we can then treat them as numbers because semantically we can say, okay, what is a cutoff and what is less than that, higher than that, and so on. There are some ways of taking domains or categorical values that are not naturally ordered and associate numerical values with these categories based on the training examples. For example, target statistics would say take the expected y, okay, for the training examples with the current category C. Okay, that gives you a number, the expectation of the y values um, for these tuples with the category C. People do that. It works sometimes. It does have the risk of leaking too much information about the target value, about your training set. Okay, that gives you a risk of overfitting. And there are several research efforts practical effort on how to accommodate, how to deal with this leakage of information, and we'll mention the cat boost algorithm that is designed to deal with this information leak. Okay. What about text attributes? Here you can have several options. You can say, okay, let's apply some text embedding, which means that basically we associate every text value or every sentence, depending on what kind of text do you have in the attribute, and map it into k numerical attributes. And then we have k numerical, it's a vector of the size k. We can treat it as k numerical attributes and then split based on them as if we have numbers, which is fine, but it doesn't always work because each individual attribute does not necessarily make sense. So if you apply some access to this attribute, it's not clear that you get something that has a clear semantics. Um, Actually, this is a known and studied research problem. What is the meaning of every or individual uh, attributes, individual numbers, individual columns in text embedding? But even if there is some, hidden semantics in every individual column, it doesn't necessarily lead to interpretable models. Okay, so it's not always a good solution. Another way is basically having a more sensitive kind of conditions, looking at our text as a bag of words. Bag of words means basically that we have a set of words, each associated with its frequency in the text. And you can have conditions like, the word X occurs at least tau times frequency of the words. So I'm not really getting into this challenge. I'll say that there are various techniques and various papers. Here's an example of one that deal with the question of how to split based on a textual attribute. Okay, now let's talk about gain function. So we have our training set. This is an important notation. We have, if S is our training set, we denote by S V in brackets the set of training examples that reach V when you apply the decision tree to them. Okay, so when you take a tuple V and you start walking the tree, take a tuple T and you start walking the tree, you reach V. If V is a leaf, then it ends up at V. If it's not a leaf, then it further grows to the subtree under V, but it visits V at some points. So basically, it meets all of the conditions up until V. That's SV. Now, natural gain function would be to say, well, if I used V as a leaf, then let's look at all of the examples that end up at V. And I would need to make one uniform decision for all of these. What is the error that I would gain there? The loss of accuracy, loss of precision. I can also split it to UI to UD, and then my error would be the sum of errors for each of my children UI. Okay, so your decision is compare what you would use, what you would lose for SV, to what you would lose from splitting V into U1 to UD. And that's your gain. That's what you gain, the reduction in your error. And again, error of SV or S prime in general penalizes the set S prime for being overly or having a uniform distribution of values. But then if you make a uniform decision, that means that you are low accuracy. Okay, and we'll see some examples. So if you have your mean of the yi or they have the median of the yi, we have here some notation. So you can look at the mean squared error, which is the average difference square from the mean or the absolute value of the difference from the median. Okay, and these are examples with theoretical justification that there are some assumptions that these are basically the optimal decisions. Okay. Um, you can also look at the error functions with the classification. And basically, these correspond to the amount of information that you have in the set, how uniform or how similar the categories are. So if we have the set S prime, we denote by S prime C the set of examples where the label is C. So PC will be the fraction of the examples of S prime having the label C. So you can look at the information, the entropy of S prime. Okay, you sum up over the PC, treating them as probabilities, and multiplying them by the inverse of the log of the probability. Okay, or Gini, which has a similar intuition, but you multiply PC by the complement of the PC, and these are functions that get their maximal value when your distribution is uniform. But then making a uniform decision is bad, right? It has a high cost. That's the intuition. Okay, some stopping criteria for a leaf. So when would you decide not to split a leaf? Well, you can say, okay, if all of them have the same label, then I'm good. Or I don't have any split condition. I search and I don't have any split condition that I can actually give me any gain, or this gain, or say you cannot even separate the SV in this example. But even if I can separate, I don't have any gain or too low of gain. It may be the case that you have too few examples. Okay. And you want to say, okay, I'm not going to split based on these very few examples because that will lead to overfitting. Or you say, well, I'm willing to live with up to some maximum depth of the tree. I'm not going above that. So if you reach some maximum tree depth, then you can say, okay, that's where I'm stopping. Okay. Now, another technique is basically simplifying in post processing. Okay, so you take a tree and you may look at it, in a general perspective and say, well, now that I look at it, I don't really need all of this subtree. Let me collapse it back to 82. Now, you would do that to improve your generalization, right? To reduce overfitting. So one technique is using the validation set in the reduced error pruning, which is very simple. Take your validation set, not the training set, the validation set, and go through your nodes in some order. And at each time, just simply test what is the accuracy with the current tree, and what is the current tree, what is the accuracy with my subtree under V collapsed into one single leaf. If you're better off, then collapse. Okay, that's a very simple technique. Okay, but the idea is that you're not trying using a training set, because in your training set you will probably lose because there was a reason why you decided to split stuff. But in the validation set, that's a different story. And that's an example of how we are using the validation set. Here's another example: cost complexity pruning. So here you're basically saying, well, let's look at our tree. Again, a general perspective. Now we take a node V and we say, okay, again, what is the error of using every single decision for SV minus what I'm actually getting by looking at all of the leaves under a tree? What is my gain? Well, I also normalize it by the number of leaves, okay, which think of it as a way of measuring the complexity of the tree. If that's not too much, if I'm not losing too much, then I decide to collapse. What does it mean too much? Well, I use here some hyperparameter alpha, okay, to help me decide whether I'm losing too much or not. So you can see here an example from the documentation of scikit-learn, where you're basically saying, well, what should be alpha? If I'm using alpha that is low, then I'm, losing a little in the training example, but I'm starting to gain actually in the test because I'm doing less overfitting, right? I'm reducing my bias. Okay, and you can have a higher and higher alpha, which means that you'll be pruning more aggressively or collapsing more aggressively until at some point you will over collapse. You will over simplify. Your bias will be too high, and then you will start actually losing a bit in the test set. Okay, so there's some sweet spot where you want to be and choose a good alpha. That's the idea. Okay, we're done with the decision trees. Next, we'll look at ensembles of decision trees.